Okay, good morning, everybody. So we're taking a look at electron representations, and this is 2.3 of your Discovery education, and we're taking notes on Explore number 1. So let's go ahead and write out our Cornell notes. And I'm going to put down today's date, Friday 10/27, Friday 10/27. Again, make sure you leave enough room for you to write notes to yourself, side notes, questions, etc., right? Our essential question: what is the configuration of electrons within an atom? What is the configuration? That's kind of like saying the structure, how you set something up, of electrons within an atom. Within an atom. Question mark. Okay. Now, I'm going to encourage you to, for a moment, pause your video and go ahead and write down what you know. Okay. So take a moment and just jot down a couple points. All right. I'll be looking for these points inside your notebooks. Okay. What do you know? Okay. Hopefully you paused and you wrote down some of the things that you already knew about that. So when you take a look at our notes, we can see we have a few different sections. Electron configuration notation. Okay. Got a few vocabulary words here: quantum number, electron configuration. We've got a video. I imagine it's going to show us about electron configurations. A second video on lithium. The first one was helium, and another one was on chlorine. So they're giving us a number of different examples to help us out here. And then we have a section on writing electron configurations. They're going to talk about the Pauli exclusion principle. That should remind you of the Aufbau principle and the Hund principles. These are things related to filling electron configurations. Electron behavior video segments. These two segments here are ones that came from the last Explore, and some additional reading, and then using the periodic table. That seems to be our third. And then noble gas notation. All right, so we got about 4 sections that we're going to be taking notes on out of this Explore number 1. Okay, so let's start with Roman number 1. Electron configuration notation. And you can see the main ideas in green. To study the properties of an element, scientists consider where the electrons are located within an atom. Okay, so it seems like there's a relationship here. The properties of elements is related to the location of electrons, to electrons and their distribution, location and their distribution. Okay. Now we jump into kind of an argument here. Quantum theory uses specific rules to describe the location of the electrons. I'm in paragraph 1 here. They use, I just read this one here, right? Quantum theory uses specific rules. They use shorthand methods to describe using a system of quantum numbers. All right, so that seems like that's useful information for us. Number one, or let's put down B, letter B. Quantum theory uses specific rules to describe electron locations. And specifically, they have a shorthand method. And this shorthand method uses quantum numbers. Okay, remember you had 4 quantum numbers, right? You have the principal quantum number, principal quantum number was equal to n, right? The letter n. And then you had the second quantum number, which we called the azimuthal quantum number. And this was described by this kind of funny shaped L, right? And what does this do? This describes the configuration of electrons in an atom, their shape. The shape, or AKA configuration. Okay. Then you also had the magnetic number and the spin number, right? So, for example, they give us an example here, and they say helium. Helium is 1s2. So let's just put this down here. This will be letter C. Example is going to be helium. Elemental symbol He. And if we go and open up another tab here really quickly, this might be beneficial to us. Let me just make sure this guy knows that we're on tablet mode. And here we go. And we want P table. There we go. And if we look over here, there's helium. It's number 2, right? Number 2. Okay, so let's go back over here and let's go ahead and write this down. Helium, which is got a number 2. Right? Helium has a atomic number of 2. That means we can assume it has 2 electrons. 2 electrons. And when you take a look at your notation, you write down 1s2. So you know that the 1s level can take a total of 2 electrons. Okay, this is your first energy level. This is your first quantum number. Okay, so quantum number. This is the first energy level, right? We would say that this is where n equals 1, right? And we know here that this would be your azimuthal, right? And this is telling us that it is a spherical shape, right? Okay, this is the distribution of your electrons is spherical, and you can have a maximum of 2 electrons. And so it has 2 electrons. It is maximally filled. Maximally filled, right? And we'll close that parentheses there. Okay, so keeping on here, let's see, did we cover everything in here? This system of notation includes 3 pieces of information. The first was the energy level. Check, we just talked about that. Numeral 1 represents that. The letters S, P, D, and F represent the different types of orbitals. This was your second piece of information, the orbital type, right? So I guess we could write that over here as with the orbital type. Okay. And finally, the number of electrons in each orbital is shown by a superscript after each orbital type. And we did that. We said that there were 2 electrons. We said it was maximally filled. Okay, good. So if you take a look over here, it kind of gives you a list of hydrogen, helium, lithium. So you can see how, where does my thing go when I do that? We got to figure out how to keep that pinned. Clear screen. And let's go back over here. So you can see how from hydrogen all the way to sodium, you're increasing from 1. Helium is still principle number 1. When you get to lithium, there's enough electrons. There's 2 in the N level, and there's 1 electron in the N equals 2 level, right? So you can just kind of see how it goes to boron, to nitrogen, to neon, to sodium at the very end here, Na. Okay, so writing electron configurations. Let's go ahead and write this down as Roman numeral 2, I believe. Okay, we're going to carry this little line down. And here we go, Roman numeral 2, writing electron configurations. And they give us a little thing here. They re-mention the Pauli exclusion principle. We wrote about this last chapter, but you can go ahead and rewrite it if you need to. It says that no 2 electrons can have exactly the same quantum number. Okay, you can't have 2 electrons in the same place at the same time. Now here, little side note, 2 electrons can occupy the same orbital, but each electron is assigned a spin, so it can be identified individually. Remember, we give that an up spin or a down spin. So in electron configuration notation, the first electron added to an orbital is denoted with the up arrow, and the second has a down arrow. So maybe let's go ahead and write this down here as this. We'll say number 1. When 2 electrons occupy the same orbital, comma, we denote them with opposite spin arrows. So remember, if you remember our example, we said that when you're filling an electron configuration chart, you have an up spin and you have a down spin, okay? This represents the up spin, and this represents the down spin, okay? And the Hund rule or principle said that when you fill these boxes, you first fill each box with 1 upspin, and after you've filled each section with 1 upspin, then you're allowed to fill the second one with the other half spin. Okay, so let's see here. All the orbitals of one type within an energy level must be completely filled before an electron can occupy the highest orbital that was Aufbau's principle. And finally, Hund's rule states that all of the orbitals of the same energy will be filled with one electron before any of the orbitals take on a second electron. Okay, so this, you need to write these down. Hund's rule. And this one over here, they don't mention it, but it was Aufbau's principle. Okay, is this one right here. Okay, this is Aufbau's principle. And Hund's rule is this one right here. This is Hund's rule. Okay, so we need to make sure you have those down along with Pauli's exclusion principle. So let's just move this over here. I'm going to write down letter B. Aufbau's principle. Okay, and go ahead and write down what it states. And I'm going to be looking for in your notes the Hund's rule. Okay, and so write down what that states. Okay. All right, hopefully you've had a chance to write both of those. Okay, so we're back here, and let's just go ahead and let's see, what am I trying to do now? Pen, clear screen. All right, that'll work. And we're going to scroll down here. Okay, so hopefully you've written down Aufbau's principle and Hund's rule. Using the periodic table. Okay, this is going to be Roman numeral 3, okay? Let's see here. Let's get our line. And we're going to say Roman numeral 3. Using the periodic table. Okay, the electron configurations of elements closely follow trends in the periods of the periodic table. If you jump to paragraph 2, across a period, for instance, the number of valence electrons in the last sublevel increases as each orbital is filled. And they give us examples of boron, carbon, nitrogen, oxygen, fluorine, and neon. And you can see how this was number 1, this was number 2, this was number 3. Okay, what am I actually doing? I'm circling this number 1, 2, 3, 4, 5, and 6. And if you take a look at our periodic table, this is what they're talking about. It's going from boron to carbon to nitrogen to oxygen to fluorine. Remember, if we go and we, oh my gosh, here, let's go ahead and clear the screen and do this. Make sure I'm reduced. How do we clear the screen over here? It's like I lose my thing when I do that. It's a little frustrating. Mouse, pointer, pen. Oh, here we go. I'll just go to eraser. Maybe that'll work. Yeah, that'll work. Sorry about that. And let's see if I can. What just happened here? Okay, so go here. There we go. All right. So if you take a look at your periodic table, and I'm going to click onto the electrons, you can see how these are organized actually into what we call S blocks, right? S blocks, which is going to be this group right here. You have your P block, which is going to be over here. This is your P block. It's going to be 13 to 17, right? You have your D block. Okay, this is your D block over here. Letter D. And then you have your F block, which is over here. And this is your F block. Okay. If I go back, clear the screen, and come here, this is numbered 1, number 2. This is in the old nomenclature. This was 3, 4, 5, 6, 7, and the last one was 8. This represents your valence electrons. These were your valence electrons. Okay, so your first period, try to clear this here. Your first period, period 1, has 1 valence electron in it. Your row 2 has 2 valence electrons in it. So this would be like saying you have 1s1. This one would be like saying 1s2. Okay. Your over here, this represents your first P. So this would be like P1. This would be P2. If we were to actually talk valence electrons, though, the first group is 1 valence. The second group has 2 valence. 13 has 3 valence, and you can have up to 8 valence electrons. Go ahead and sit anywhere, guys. Okay. All right, so that's kind of what we're talking about with the periodic trends. And there's probably something else that we need to do. So let's clear the screen. If you look at things horizontally, this group right here is your first row. Your second row is here. Sorry, this keeps on going out. This is your second row all the way to the end. This is your third row, right? And on. You can go all the way down to your fourth, your fifth, your sixth, and your seventh. Okay, and what these relate to is these relate to the number of energy levels. All right, so let's go and write this down. Your rows equal energy levels. You might say that you have an atom, and your atom can have either 1 energy level, 2 energy levels, 3 energy levels, 4 energy levels, right? So I could write this down as 1, 2. This would be 1, 2, 3, and 4. You can go all the way up to 7. These would be your energy levels. They equal the period or the row number. Okay. Now, how many electrons are on your outer shell? Your valence, if you have an atom, and this is your highest energy level. If you're in row 1, like hydrogen, you would have only 1 valence. If you were in, and I'm going to clear my screen here, if you were in row 2, or not row, column 2, you would actually have 2 electrons. If you were in the third group or family, you would actually have 3. Let's use a different color here. You'd have 3 valence electrons. And so you can fill all the way up to a total of 8 valence electrons. And your periods, this would be your group number equals the number of valence electrons. Okay. All right, so let's clear our screen. Let's see where we are on all this, okay? Clear the screen again. Okay. And that leaves us only with the last part here, which is our noble gas notation. Okay, so this is going to be number 4. Okay, and I'm going to hit pause here for a second, okay? Okay, and finally, we're on noble gas notation. I had to just do something there. So what happens when you're taking a look at some of these elements and you got some elements like, oh, I don't know, we could say you had silver here, and silver has 47 electrons. I mean, I could write that down. Let's just first say, what do you do when you have to write out long configurations? Do I really want to go ahead and write down 1s2, 2s2, 2p6, 3s2, 3p6. So how many do I have? 2, 4, 10, 11, 12. That's 18 electrons so far, and I got to do 47 electrons. That's going to take me forever. Well, no, you can actually have a shorthand, a little shortcut method. And what you do is you take a look at the, clear the screen here. If you go, clear the screen. If you go to here, AG was right here. So you go all the way to this very last column here. These are your noble gases. You could take a look at the one that's right above it, the row above, and you could go ahead and say KR. Sorry, a lot of interruptions here this morning. You could take the noble gas that's above one line here. So I'm talking about this one right here, and say KR. And then you could basically just go ahead and fill out the configuration underneath it. So you could go ahead and say that, all right, KR. And let me just see if I can clear my screen and go back and scroll over this way here. So then I'm in energy level 5. So I could write down 5s2. That took care of that. What's the next level that's going to get filled out? Clear the screen. Sorry, clear the screen. So there we go. KR was 36, right? This had 36. So that's 37, 38. How many do I need for gold? I need 47. So I need 47. 36, 37, 38. So I'm going to do all of my P's over here. So this is going to be 5P6. 5. What comes after? You have the S, the P's, and the next one you have are the D's. Got to pause again here. Okay, you can tell I'm recording this in the morning and people are coming in late. 5S, and you can have up to 10 in there. How many do we have? 36, 37, 38, 39, 40, 41, 42, 43, 44. I need 5. I need 3 more of these. So there you go. And that would be your notation. And that's a lot shorter than having to draw out this whole thing here. Okay, so this is called your noble gas notation. All right. So I think that's it. We're going to go ahead and pause it, and I will go ahead and let me just kind of come up here really quickly because I think I might have some time. Go this way. And let's, geez, don't want to do that. Undo. Undo. There we go. Let's go back over here a little bit, okay, because I think we have a little bit of room to run with this. So I want to take and consider this thing here. Okay, so if you're going to fill out your energy levels, and we call this your 1s, and then your next level is your 2s, and then we say you have a little half step over here where your 2 P is, and you have 3 boxes.